Right, so what I'm going to talk about now are arrays of springs. So an array is basically an arrangement of similar objects. So in this case, an array of springs gives us two primary options for arrangements. We have what we call parallel, where the springs are parallel to each other, and series, where they are in a line, linked end on end. You can also do like more complex arrangements and have like one spring here and then have another spring here connected to another spring, and you can have more complex arrangements. You're not generally going to see this in AP Physics 1. We don't even really see this much in Physics C, but it is possible. So what we want to do is we want to come up essentially with a way to describe the kind of net spring force, the net displacement, and so forth. So we wanted to find something called the effective spring constant. We call it K with a subscript EFF for K effective, the effective spring constant. And this is essentially the spring constant that if we could replace the array with a single spring, then it would give you the exact same displacement and net force. So it's basically based on the overall force of the array times K effective times the overall displacement delta X. So this is like the net force, and this is like the overall total displacement for the array. So if I'm looking at these different situations, I have a single spring here. I have these two arrangements. So I would call this the K effective, is if I could have one spring that I could replace this pair of springs with, so that whatever stretch this block has from its equilibrium state, so say its equilibrium state is here, so that there is a delta X here, that essentially the net spring force that is felt, so if I picture this mass mg as having a gravitational force down, then there is some net spring force due to these two springs. And that if I have this net spring force, that would give me that overall delta X based on this. And then this guy over here would basically have the exact same delta X. It would have the exact same spring force for that gravitational force. So that these two diagrams, these two displacements are the same, but I want to know what value of K would I have to make these two situations equivalent. Or in this case, if I have these springs resting here, and there is some overall displacement here, delta X, and then there's some net spring force acting on that block with that same gravitational force, what would that situation be? Now, if this is the same K1 and this is the same K2, would this overall delta X and with that overall spring force net, what would that need to be the same? So what we can do is we can make some assumptions in these two different cases so that we can figure out what is the effective spring constant. And that effective spring constant is going to tell me how these are related. Well, when you have an array in parallel, there's one big assumption that we make. And when our array is in parallel, we assume that the delta X for each of the springs is essentially equal to the overall delta X for the system. So that is the assumption that we make over here in parallel. So that they're going to have different spring constants. So if I define spring force 1, so if I look at what's going on here and I take a look, there's two springs acting up on this block. So block M. So I have spring force 1, and I have spring force 2, and I have my gravitational force mg. So spring force 1 would be the spring force just due to that spring. And it's going to be K1 times delta X1. And then I can define my spring force over here as equaling K2 delta X2. And then I can define essentially that by looking at this equation, that spring force 1 plus spring force 2 must equal the gravitational force here. Because if this is in equilibrium, those have to add up to be true. So then if I take a look, if I replace spring force 1 with K1 delta X, 1, and spring force 2 with K1 delta X2, K2 delta X2, then essentially what this tells me is that I can factor out this X1 and X2 because they're actually the same. Those are actually the same. So I can rewrite this as K1 delta X total plus K2 delta X total. And that's going to equal mg. So I get K1 plus K2 times delta X total is equal to mg. But I know that if I want an effective spring constant, that my effective spring constant times delta X total needs to equal mg, because that's what the effective spring constant tells me. That I want to have that same delta X total balancing out that same gravitational force. So this tells me that when I have parallel springs, that my effective spring constant is the sum of K1 and K2. So that is always going to be true for parallel springs. So for parallel springs, we assume that the displacement for each spring is identical and that the effective spring constant is K1 plus K2. So that's parallel springs. Well, what about the series? So what does that tell us? Well, this one's a little bit different. This one's actually more complicated. So if we look at what's going on in that one, there's an overall net delta X for this, but if I picture what's going on, basically, let's see, get a different color. Like this one is going to have some sort of delta X1. And this guy here is going to have some sort of delta X2. And the assumption is that delta X1 plus delta X2 adds up to be delta X total. And the only way that works is that the spring is in equilibrium. So if we were to look at kind of what's going on with this middle spring, so here's this middle spring here. So this middle spring on the bottom has like gravitational force pulling down, and it has the spring force of spring 1 acting on spring 2 pulling up on it. But I also know that the spring force by Newton's third law of 1 on 2 has to equal the spring force of spring 2 on 1, but they'll be in opposite directions. Because the spring force from at the ceiling here has basically some on this spring is going to have some force at the top due to the wall, and then it's going to have the other spring pulling down on it. So basically what this tells me is that the spring force for spring 1 has to equal the spring force on spring 2. And that actually also then has to equal the net spring force. Actually, so that equals the net spring force. Whereas over here, in the parallel case, we said spring force 1, I erased that part, plus spring force for the second spring has to add up to equal our spring force net. So if we take a look at that assumption, if I do delta X1 plus delta X2, over here we can figure out how our K effective works. So I know that my spring force 1 is equal to my spring force 2, which is equal to my spring force net. So I know that FSP1 is still going to be K1 delta X1. FSP2 is going to be K2 times delta X2. So if I want to, I can solve for delta X1, because it's going to be FSP1 over K1, and delta X2 is going to be spring force 2 over K2. And I can use this equation that delta x1 plus delta x2 is equal to delta x total. Well, delta x1 is going to be FSP1 over K1. Delta x2 is going to be FSP2 over K2. And then if I come back over here to my definition of K effective, I know that FSP net, in our case, is going to need to equal delta x total times K effective. Okay, that's just our definition over here. So our delta x total times K effective tells us that delta x total is going to be our FSP net over K effective. So I can sub that in over here. But these three forces are all the same. These are all the same. So I could replace them all with FSP net, which means I could factor out an FSP net and divide it out, and I would get 1 over K1 and 1 over K2 and 1 over K effective. So what that tells me is that 1 over K effective is going to be 1 over K1 plus 1 over K2. And I can extend both of these equations to include like 3 springs or 4 springs if I wanted to. You generally won't see that. This one really means, because I haven't actually solved for my effective spring constant, it's really 1 over K1 plus 1 over K2 to the negative 1. So this is your effective spring constant in series. This is your effective spring constant in parallel. So basically what that means is you can always represent just all of this spring force just as a single spring force. And then I can just define, oh, my K's are in parallel. So I can define my spring force for this case. And I can say, oh, well, my net spring force is going to be K1 plus K2 all times my overall delta x total. And I can figure out what that displacement is. And I could do the same thing over here with this example. So you can use this in different ways. And I think there's an example or two of this on your homework assignment for this unit. You're going to see this type of situation again when we get to circuits, and resistors in series and parallel will act very similar to this. So just in general, what this tells me here is that if I add more springs, no matter what their values are, I'm always going to get a larger spring constant. So since my gravitational force is equal to K effective times my displacement total, in this case, my gravitational force doesn't change depending on the number of springs that I put in place. But if my K effective increases by adding more springs, then in order to have this add up to be mg, then the overall displacement of each spring is going to decrease. So for example, if I have a bunch of weak springs that have very low values of K, and I'm worried about, say, overstretching them and putting them past their elastic limit, if I put the springs in parallel, then each of them will get only part of the stretch. So that's kind of handy. Over here, this one basically says the opposite. This actually says that if I put these things into series, that they are going to have an overall lower effective spring constant, and that they're going to end up keeping whatever stretch they're going to get, because they're going to all stretch out to equilibrium. So they're each going to experience essentially mg's worth of force. So this one be kind of funkier for each of the springs. And basically you could get more displacement overall because the displacements are going to add up to be whatever the total displacement is, because each spring is going to experience mg's worth of spring force. So in lots of real situations, like things like with suspensions and so forth, a lot of cases like suspensions on a bike or suspensions on a car. They may have multiple springs present, sometimes kind of as backup to make sure if one spring goes out, there's another spring there for it. But also just because you get these set manufacturer springs and they might not have the exact same spring you need, so you can always create an array of springs to get whatever value of spring constant you need for whatever your purpose is.